This is 12.2.5 wave-particle duality. So, the true nature of waves is neither described fully by the particle theory or the wave theory of light. So we say that light has wave-particle duality, has both properties. So the photoelectric effect demonstrates particle behavior. And diffraction and interference demonstrates wave behavior. So if it's got both properties, we call this wave-particle duality. If you recall back to particle and quantum physics in year 1, I mentioned that light has no mass, and yet it still carries momentum. So this is something that was quite perplexing to year 1 students, because they thought, well, momentum is mass times velocity. So how can it have momentum despite not having a mass? And this was described by Einstein in one of his equations. So his equation, the full version of it, is E is equal to the square root m squared c to the 4 plus p squared c squared. So let's see what happens to this equation during different situations. Let's take some mass, for example, some stationary mass. Think of maybe a metal block. It's got some mass, it's not moving. So a non-moving metal block has 0 momentum. So if we plug that into the equation, it's got some value of mass, so there is m squared, and c to the 4 is just a constant, plus p squared c squared. P, because it's stationary, is 0, so the p squared c squared term disappear. You end up with square root of m squared c to the 4. If you evaluate that, it's E equals to mc squared for stationary matter. Now the same can be said for light. If we have light, a photon for example, the photon does have energy. So E, the energy, is a non-zero value, equals to square root of m squared c to the 4. Well, light has no mass. So m squared c to the 4 terms disappear. And then you're left with square root of p squared c squared. You evaluate that, you get energy is equal to pc. So if light has energy, then it has some momentum, despite not having any mass. And that's described by this equation here.
What's P?
P is momentum. So, since light has no mass, the equation simplifies to E equals to PC. This is the momentum of light. For stationary matter, and that basically means P equals to 0 if it's stationary, the equation simplifies to E equals to mc squared, which you already know. Start a new page. We'll now look at the Compton effect. So in the Compton effect, we have a target electron and we have some photon that is incident with the target electron. This incident photon has some energy. And since it has some energy, it has some frequency. So it's got E1 equals to HF1. When this photon is incident on the electron, it causes a deflection in the electron. So our electron becomes scattered. And a photon also becomes scattered. These two create their own angles to the horizontal, so two different angles. It's possible to have them the same, but they don't have to be the same. And what we observe is that this scattered photon has a different wavelength than the original incident photon. Its wavelength increases and its frequency decreases, so its energy decreases. So it's got E2 is equal to HF2. And here we can say that F1 is greater than F2 and lambda 1 is less than lambda 2. So the frequency went down, the wavelength went up of the scattered photon, and so the scattered photon had less energy. So by knocking into an electron, the incident photon gave some of its energy to the electron. The electron then gained momentum both horizontally and vertically. So in this diagram, you can see it's gained the horizontal momentum to the right. It also gained some vertical momentum upwards. The scattered photon carried on having some horizontal momentum to the right, and it had some vertical momentum downwards. So the vertical momentums cancel each other out, and the sum of the electron's horizontal momentum and the sum of, so the horizontal momentum of the electron and the horizontal momentum of the scattered photon will be equal to the original momentum that the incident photon had before striking the electron. So momentum is conserved. So despite the photon having no mass, it caused a change in momentum in the electron. The scattered photon lost some energy, I'll put in brackets, given to electron. So its frequency became less. The momentums before and after the collision are equal, so momentum is conserved. So the momentum before was P1C is equal to the momentum of the electron, which is ME times V, plus P2C. Now, if energy is equal to Pc, and the energy of photons is also equal to hf, or the alternative version hc over lambda, we can equate these equations together. So E is equal to Pc, and E is equal to hc over lambda. So if we put these together, we've got Pc equals to hc over lambda. The c's then cancel out. So you're left with P is equal to h over lambda. That can then be rearranged and it gives us the Broglie wavelength. So lambda is equal to h over p. For matter, so things with mass, their momentum is also equal to mv. So for matter with mass P equals to mv, so we end up with lambda equals to h over mv. So even things with mass exhibit wave-particle duality, and he called these matter waves. So because matter can behave like waves, that can lead us on to another experiment that shows wave-particle duality, but this time showing the wave-like behavior of things we usually consider as matter. So we'll start a new page. Electron diffraction. So the experiment done by Davison and Germer is much like doing an experiment using a laser and a diffraction grating. Only, instead of using a diffraction grating, we use atoms in a nickel plate, and instead of using a laser, we use a fine beam of electrons. So we've talked about a fine beam before, and the electron gun. So this is a Davison and Germer experiment. So if we've got a nickel plate, and we have a beam of electrons, the atoms in the plate behave like slits. So it behaves like a diffraction grating because there's many atoms, there's many slits. That causes electrons to diffract. And strike a screen. If we looked at the plane view of the screen, so I'm going to draw the screen in the plane view. We'll see this effect as rings. So this is called a diffraction pattern.
What's the difference between a diffraction pattern and an interference pattern?
Interference pattern happens in a double slit. The diffraction pattern can happen in one slit, multiple slits. So they used a fine beam of electrons generated by an electron gun and accelerated through an anode voltage V. So we use the electron gun equation first. EV equals to a half mv squared. And if you increase the voltage, you'll end up increasing the velocity of these electrons. So increasing V increases little v. If we then multiply both sides by m, we get MEV equals to a half m squared v squared. We can rearrange this to get the momentum. So 2 MEV equals to m squared v squared. And square root of 2 MEV equals to mv. And mv is just momentum, so we can substitute that into the Broglie wavelength equation. So lambda is equal to h over mv, and that gives us lambda is equal to h over the square root of 2 MEV. So increasing V will decrease lambda because V is on the bottom term. Increasing V decreases lambda. Then, considering the equation, and this is again from last year's equations in waves, n lambda equals to d sine theta. If you increase the potential difference, then the wavelength decreases. And if the wavelength decreases, but d, which is the slit spacing, remains the same, then sine theta has to decrease. If sine theta decreases, that means theta needs to decrease. And if theta decreases, that means that your rings become closer together. So increasing V decreases lambda and causes the rings to become more tightly packed. Or we could say closer together. Because theta decreases. And that's the end of 12.2.5.